All right, on to section 3.5, linear systems of equations. So some familiar stuff from linear algebra, but we'll put a few new twists to it. Recall that we'll represent a system of n linear equations and m unknowns in vector and matrix form. Ax equals b. A is an n by m matrix. For each row of A, there corresponds an equation, a linear equation. For each column of A, there corresponds an unknown. So A is an n by m matrix. X is an m vector of the unknowns, x1, x2 through x sub m. And B is an n vector, if you look at the dimensions, one entry of B for each row of A for each equation. So B is an n vector. So the dimensions line up as expected. Usual stuff, just a matrix vector representation for a system of equations. First, some familiar vocabulary. System of equations, Ax equals b, is said to be a homogeneous system if the b vector is the zero vector. So all those equations in the system of equations is set equal to 0, homogeneous system of equations. We're interested in solving systems of equations. Some systems of equations, as you know, have solutions and some of them don't. Homogeneous systems, of course, always have solutions. We could always use x as the zero vector. But we'll delineate between systems of equations with and without solutions. Definition, if there is a solution, x, to the system Ax equals b, then that system is consistent. All homogeneous systems of equations are consistent for the reason just explained. If there's no solution to the system of equations, then the system is said to be inconsistent. Okay, and you've solved these to no end in linear algebra. As you know, a consistent system might have a unique solution or it might have multiple solutions. And you have a very mechanical process by which you do the row reduction and you actually find the systems of equations. So you've dealt with this at length in linear algebra, and mechanically you know how to deal with this. We won't do any of that in here. This is a graduate level class of actually solving systems of equations. But we will talk about types of systems of equations and introduce a new matrix that's related to systems of equations and discuss them in the settings of column spaces and null spaces, primarily, of given matrix A. Okay, if in the system Ax equals b, if A is invertible, so it'd have to be square, have to be full rank, then there's a unique solution to the system, and we can see what it is. It's just x equals A inverse b. So if A is invertible, we just multiply both sides by A inverse on the left, and x must be A inverse b. So unique solution, there's what it is. Okay, so in a sense, we're not really interested in these types of systems of equations. These are, the story's over with those kinds of equations. A consistent system, so one with a solution, Ax equals b of n equations and m unknowns, so we're taking A to be n by m, is underdetermined if the rank of A is less than m. Okay, so m is the number of columns in A. It's called an underdetermined system if the rank of A is less than m. Putting this in a conversation appropriate for linear algebra, you'd think of the rank of A as the number of pivots of A if we put it in a row echelon form. So we could go through and find the rank by counting pivots in a row echelon form. Okay, well, you're saying here that there aren't as many pivots as there are columns. And you know what that's going to lead to. It's going to lead to free variables in the system of equations. Underdetermined will ultimately imply, as we're about to see, that there's not a unique solution. Now, we did get into this And we're using this term underdetermined in the setting of a consistent system of equations. So my prediction, given linear algebra experience, is has a solution and is not unique. Thus the term underdetermined. And that's what the next result says, Theorem 3.5.1. If AX is an underdetermined system, then there's an infinite number of solutions. We know there's at least once because the word underdetermined is only used for consistent systems. So, to a proof of that, okay, so let's prove that. All right. If AX equals B is an underdetermined system, A is in by M, then since the system is consistent, underdetermined includes consistency, then there exists one solution, X sub 1. That is, there's an X sub 1 such that A times X sub 1 equals B, simply from the definition of consistent. We're going to find a second solution and use that to find an infinite number of solutions. Okay, rank of A is less than M. I'm sure we'll use that because it's part of our hypotheses. It was part of underdetermined. Rank of A is less than M. A has M columns. One of the exercises will then allow you to show that the columns of A are not linearly independent. All right, so we can find a dependence relation. We've done this several times before. Let A1 through A sub M be the columns of matrix A. If these columns are not linearly independent, then they're scalars, S1 through S sub M, S for scalar. Not all of which are 0, for which a linear combination of the columns with these scalars produces a 0 vector. It's a dependence relation. All right, take vector S to be the vector in Rm that has these scalars as its components. So we can talk about this in terms of trying to get to the system of equations. I'm trying to get to the AX stuff. And define X sub 2 to be S plus X sub 1. All right, now here comes the system of equations stuff written in terms of the matrices. So we're defining this X sub 2. It will be a second solution. Let's take A and apply it to X sub 2. All right, AX sub 2, substitute S plus X sub 1 in. Distribute, property of matrix multiplication. Hey, A times S, that's a 0 vector. I mean, we just saw that if we take these components of vector S and take them as coefficients, respectively, of the columns of matrix A, then we get the 0 vector out. That's where the S's came from. Okay, hey, when you do A times S, A is a matrix, S is a column vector, that gives you a linear combination of the columns of matrix A with the components of vector S as coefficients. We've done that before. So indeed, AS actually is this particular linear combination. So that produces this 0 vector, AS equals 0. AX1, where'd that come from? Assuming X1 is a solution. So we get AX1 equals B, a solution to the original system of equations up here, AX equals B. So AX1 is B itself. Add that to the 0 vector, we get B out. And we just saw that A times X sub 2 equals B. That is, X sub 2 is also a solution to the system of equations. So we found one solution, X sub 1, based on the definition that underdetermined means the system is consistent and so has a solution. We use the second hypothesis, underdetermined means rank of A is less than M, to set up a linear combination here. Notice this S vector is not the 0 vector, so S plus X sub 1 is indeed different from X sub 1 itself. And we found a second solution. Now we're going to find, based on those two solutions, almost in a geometric way, an infinite number of solutions. Let W be a vector in R. So any vector, let W be a scalar in R, any scalar, and consider X sub W to be Wx sub 1 plus 1 minus W times X sub 2. All right, I claim there's geometry behind that. So think of W as like a parameter. There's no constraints on it. I guess it could be any real number. So think of it as ranging over the real numbers. Think of it as ranging between 0 and 1 first. When we plug in W equals 0, we get out this vector is, we got 0 there, x sub 2. 0 times x sub 1 plus 1 times x sub 2 when W equals 0. So when, I actually like to think of W as a parameter t like time. So when is the right thing to say. When W is 0, x sub W equals the vector x sub 2. When W equals 1, we'll get out 1 times x sub 1 plus 0 times x sub 2. So when W equals 1, this vector we're choosing is the x sub 1 vector. And for W between 0 and 1, in a sense, we're getting vectors between x sub 2 and x sub 1. Were we to plot all of these vectors, x sub W, as W ranges over the all real values, and we put these vectors that result in standard position with their tails at the origin, their heads would trace out a straight line. So we're getting a straight line. I want to say that passes through the heads of x sub 1 and x sub 2. This is a straight line in R. Where does x live? To find the dimensions, let's see, we're doing n by m, so x would have to be n by 1. So we're in Rm here. So we're getting a line in Rm. And that's being produced as you think of this parameter, W, as moving across real values. But we're getting a line out, a line's got a bunch of points on it, and those points correspond to vectors in standard position. So there's geometry behind it. Just got to be very, very careful of going from the vector conversation to the line conversation with the obvious caveat of standard position. I got to put vectors in standard position. If you do that, yeah, this is a line in Rm. All right, and we're about to show that every one of these x sub w's, which corresponds to points on a line in Rm, yield a solution. So let's take Ax sub w. X sub w is defined like this, so we'll substitute that in. Okay, use our distribution, pull scalars out front. So we'll get w ax1 here. I know what ax1 is. We'll get 1 minus w ax2. I know what ax2 is as well. All right. So properties of distribution of that matrix multiplication. Ax1, x1 was a solution. Ax1 is b. We'll get a b there. X2, ax2. X2 was a solution. We know ax2 equals b as well. So we've got a b from this and a b from that. That's the two solutions we had. Now you've got these little w parameters. W is a coefficient of the first b. 1 minus w is a coefficient of the second b. The wb and the minus wb cancel to leave us with 1b. We just showed axw equals b. So x of w is also a solution to the system of equations, ax equals b. How many such w's are there? Many. There's one for every real number. There's uncountably infinite number of such solutions. Implicit in this, we've shown if there's two solutions, there's an uncountably infinitely many solutions as well. Okay, so we've got infinitely many solutions. In an underdetermined system is what we've shown specifically. All right, and you kind of already knew that. Think of how you solve these things. Let's see, I'd do the row reduction deal. If we've got a consistent system, then solutions exist. Underdetermined, this is gonna imply this rank of A is less than M thing, less than the number of columns, is going to imply there's columns of A that are pivot free. And those correspond to free variables, much like the W acted in some sense like a free variable. So not at all surprising given your linear algebra experience. In the event that we have a bunch of solutions to choose from, we might want to choose a best solution, maybe that optimizes some other stuff. You've got a system of equations that has solutions. It's underdetermined among that collection of solutions. According to some criteria, choose a best one. So anyhow, we do have existence of solutions. We might add additional conditions to make it better determined in a sense. We might need to add conditions related to more linear equations. We could add more linear equations as long as we keep the system consistent and maybe choose a best solution with respect to some other parameters. But we are dealing here with the existence of a solution. We'll see here in a little while, well, we'll see right now, what it means for a system to be overdetermined. So the punchline here is going to be there are no solutions. All right, well, we might want to get close to solutions in a sense. In the previous one, things were great. We had solutions coming out of our ears. We had uncountable number of solutions. A system AX equals B of n equations and m unknowns, where n is greater than m, and the rank of A augmented with B is strictly greater than the rank of A, is called overdetermined. All right, so previously underdetermined, bunch of solutions. Overdetermined, no solutions, as we're about to argue. So there's the definition. And we'll take a different approach on, well, what are you going to do to pick a solution? There's not a solution. How are you going to modify the game to pick something that's appropriate? And this is where the statistical stuff will come in, potentially. In an overdetermined system, the rank of A augmented with B is strictly greater than A, means B's not in the column space of A. The rank of A is the dimension of the column space of A. You add this new column, you get a rank that must be one greater than the rank of A, if we do get this strict inequality. So we've got a different column space. Yeah, it's got a new dimension, and that new dimension is contributed by vector B. We've actually in the past seen situations where we would have the rank of A augmented with B equal to the rank of A, in which case we drew the conclusion that B must be in the column space of A. Here, we don't have equality. We don't have B in the column space of matrix A. So there's no solution to the system of equations AX equals B. What's up with this? What's that got to do with column spaces? We've done this a bunch. Oh yeah, AX, this gives a linear combination of the columns of matrix A with coefficients given by the components of X. It's a linear combination of the columns. It's something in the column space. Well, B ain't in the column space. All right, then there's no X that makes this little equation true. So in overdetermined systems, no solutions. Given no solutions, we might look at approximating a solution. Approximate a solution. One approach to this is method of least squares. We might look in RM for a vector B that just is minimal with respect to how far it is from potential solutions, or how it best approximates this output. Anyhow, in the event of no solution, we're going to maybe do some type of approximation of solutions, and would do a best approximation with respect to something, least squares. We won't have time. This is in chapter 9. In this course, we won't have nearly enough time to get to chapter 9. All right, a new idea, all that stuff was, probably all of that stuff was from sophomore linear algebra. I know the words overdetermined and underdetermined pop up. How much time you get to spend on them in linear algebra, I don't know. But there's certainly topics from linear algebra. The following is not. All right, a matrix G such that A times matrix G times matrix A equals A is called a generalized inverse of matrix A, denoted G equals, I'll just read it, generalized inverse. Okay, nobody said nothing about A being a square matrix. So this generalized inverse will work potentially for non-square matrices. If A is n by m, then a generalized inverse of A must be m by n for the conformability of the related matrix products. That's where that comes from. The dimensions have to be right for the matrix products to exist, in other words. If A is non-singular and so invertible, then generalized inverse can be taken to be A inverse itself. So when A inverse exists, we could put an A inverse here, and of course, A times A inverse times A equals A. So in that sense, this G thing is a generalized inverse. When A is invertible, we can use A inverse itself. What we won't see until the next section is these generalized inverses, they actually exist. So you take any matrix A, it has a generalized inverse. It may not be unique, but generalized inverses do exist. Sit tight, we'll do that in the next section. Next section, in fact, the title, I think, is generalized inverses. Some properties of the generalized inverse. Okay, this is kind of clunky to verbalize as I'm pronouncing this, generalized inverse of matrix A. But if we have a generalized inverse of A, then the transpose of that generalized inverse is itself a generalized inverse of A transpose. Okay, we'll go through these. These are rather computational and not too complicated. Generalized inverse times matrix A times generalized inverse times matrix A equals generalized inverse times matrix A. This is properties called idempotent. We had some class of matrices a couple of sections ago that satisfied this type of property. We made an observation in passing. So if I'll take generalized inverse of A times matrix A, multiply it by itself, we get that thing back. And that's a property of idempotent, common term from group theory. An element is idempotent if you square it and get that element back out. Has implications about the diagonal entries of a multiplication table of an idempotent group. But anyhow, the claim is simply that equation. This is potentially convenient. The rank, leave it all on the page at once, rank of generalized inverse of A times A is the same as the rank of A. We're going to look at in the last two, this matrix, the identity minus the generalized inverse of A times matrix A. And by the way, if A is invertible, that's going to be the zero matrix. So this little highlighted matrix here, in some sense, is measuring how close the generalized inverse is to the actual inverse. And matrix A may not be square, but we're trying to multiply, in some sense, the generalized inverse and matrix A together to get an identity. That's kind of the crude, informal idea behind this. So it isn't that unnatural to look at the identity minus this product, because I'm thinking this generalized inverse deal is kind of like an inverse. So it's reasonable to look at this difference. The claim is I minus generalized inverse times matrix A multiplied by generalized inverse times matrix A. We'll have a little bit of a fascination with that product to continue. The claim is that equals the zero matrix. If we take I minus that little product, multiply it by itself, we get that little product back. In other words, this thing here is an idempotent matrix as well. Got the same kind of pattern we had up here, different matrix down here. Take this thing, highlight it, multiply it by itself, you'll get this thing back. That's the property of idempotent. The rank of this I minus generalized inverse of A times matrix A, the rank is M minus the rank of A. Remember, M came up in the conversation as the number of columns of matrix A. So the rank of this thing is the number of columns of A minus the rank of A. And you saw in sophomore linear algebra, this little amount here, this ought to totally remind you of what we call the nullity of a matrix, which I think we're about to define. All right, so let's go through proof of these. They're all fairly computational. So next, let's prove them. I'll probably have to bounce back and forth to read the statement, so I'll keep that in the background of the notes. First, we want to show the transpose of the generalized inverse is a generalized inverse of A transpose. So I'll verbalize it. Okay. We have that A equals A times generalized inverse of A times A. That's the very definition of the generalized inverse. So let's introduce some transposes. Theorem 3.2.1 tells you how transposes and products interact. You know this. A transpose equals the transpose of this product. You want to take the transpose of a product, take the transpose of the constituent parts and write them down in the opposite order. So the first, this particular A, when transposed, moves from the right to the left in the product. You can't tell because we had A's on both sides, but that's the manipulation. All right, and then we've got A transpose equals A transpose times this matrix here times A transpose. Well, this matrix here, think of it as G in our definition. That's exactly what we'd have for the generalized inverse of that matrix over there. So that thing there, the generalized inverse transpose, is a generalized inverse of this matrix on the left-hand side. That is A transpose. So that happened awfully fast. It was so easy. Next, some computations. Okay. We're trying to show that this product equals generalized inverse of A times A. You know A equals A generalized inverse of A times matrix A. That's a definition of generalized inverse. So if we take generalized inverse of A times matrix A, we can rewrite this, rewrite this A using this formula, and then we get A generalized inverse, replacing the A with A generalized inverse times A. Substitution is all it is. And then we'll associate the first two and the last two, and there it is. So a simple substitution gives that one. Rank, a claim about rank. Okay, we may have to look at some of the earlier sections and recall some formulas on rank. I trust you remember this formula on rank because it's played such a big role in most of our rank computations as of late. Theorem 3.3.5 says the rank of a product is less than or equal to the minimum of the rank of two matrices in that product. All right, so we can draw the conclusion that the rank of generalized inverse of matrix A times matrix A is less than or equal to the minimum of the rank of the two constituents, and whichever of the two you've chosen, that's less than or equal to the rank of A. This is our common application of this. Now we just need to reverse that inequality. We're claiming an equality of these two ranks. We're halfway there because we've got the rank of the product is less than or equal to the rank of A. We know A equals A generalized inverse times A, definition of generalized inverse. That theorem again, rank of A then is less than or equal to, I want to view A as a product of two matrices. The first one's matrix A, and the second one is generalized product, generalized inverse multiplied by matrix A. So that product of two matrices, and we can say that's less than or equal to the rank of either of them. We want to look at the one on the right. And now we've got rank of generalized inverse of A times A is less than or equal to the rank of A, and the rank of A is less than or equal to the rank of that product. So we can draw a conclusion of equality, right, and that's what we were trying to show. Okay, next we want to show two things. This I minus deal when multiplied by the product equals a zero matrix, and this I minus deal is idempotent. Okay, both easy computations. So the first was take the I minus deal and multiply it by generalized inverse of A times A. Okay, we'll distribute. get this times the identity matrix. Okay, and then we'll get this product upon distributing. I can drop the identity matrix from that first computation. Let's associate the last three. Why you want to associate those? Oh, that's just A. That's the very definition of generalized inverse. So we can substitute for A, this product of 3 to get this. And then we've got generalized inverse of A times A minus itself. And so we get 0 out, and that was the claim. Next, let's take this identity minus deal, multiply it by itself. Okay, let's distribute this second parenthetic part onto the identity. Okay, that'll just produce the difference, and distribute it onto generalized inverse times A. So we'll get oops, I'm sorry, we're distributing the first one. The order was wrong. Let's distribute this parenthetic comment onto the difference of the other two. So we'll have this times the identity, which produces this, minus this times generalized inverse times A. Right, there's the I minus deal and that little product. Okay, so we distributed over this matrix subtraction. All right. Okay, let's see. Oh, I minus deal times generalized inverse times A equals 0, right? So we can substitute for 0. Yeah, that was the first part. So it took me a second to realize that. That's what we showed in the first part of part 4. So this product is 0. Yeah, we just showed that. We drop that, we get the I minus stuff. And indeed, that was the claim on the other part. Okay, so that matrix there actually is idempotent. Now we're trying to show something about rank. What are we trying to show? We're trying to show the rank of that I minus deal is the number of columns of A minus the rank of A. So that's what's up next. Okay. Generalized inverse of A times A is M by M. We just saw that we get this little product to be 0. So we can take the 0 matrix, the M by M 0 matrix, associate it with this stuff here. That equals the rank of the 0 oh, I'm sorry, we're taking the 0 scalar here, aren't we? Taking the 0 scalar here and the rank of an M by M matrix of zeros here. Yeah, clear from context. Context mixed up a little bit there, but yeah, rank is a number. So this is a 0 number equals the rank of a matrix of all zeros of appropriate size. Let's make it M by M. We know that that M by M 0 matrix can be written from this equation as this particular product, the first part of the previous claim. Okay. Then we've got a rank of a product, and we're dealing with M by M matrices. Let's look at theorem 3.3.15. Apparently from this product, we're drawing a conclusion that we get something greater than or equal to rank of the first plus rank of the second minus M. And remember, this was an M by M matrix. All right, theorem 3.3.15. Let's run back to notes. Just happen to have 3.3.15 pulled up here. Sylvester's law of nullity from a couple of sections ago says, let's make it bigger. A is a square matrix. Okay, we had some M by M matrices there, right? B is conformable to the multiplication with that square matrix. Then the rank of the product is greater than or equal to the rank of the first plus the rank of the second minus the dimension of the square matrix. So for us, that was M. All right, rank of the product greater than or equal to sum of the ranks minus M for us, the dimension of that first square matrix. Okay, back to the notes. We've got, right, we've got a square matrix, an m by m matrix. See, they're both m by m matrices. So rank of the product is greater than or equal to rank of the first one in that product plus rank of the second one in that product minus m, the dimension of the square matrix. Right. Okay. So theorem 3.3.15 gives us that inequality. This doesn't involve the stuff we're interested in. We're interested in the rank of A, but we saw in part 3 that the rank of the generalized inverse of A times A is the rank of A. So we can make that substitution. So we're getting closer. All right. Our claim was, let's look at the claim one more time and see what we've got. I think this is half of the claim. Back to the 3.5 notes, trying to show the rank of the I minus thing equals M minus the rank of A. Okay, how are we doing on that? There we go. There's an inequality. We could say the rank of this is less than or equal to M minus the rank of A. Take this stuff and move it to the other side of the equation. So yeah, we are halfway there. We've got an inequality pointing in a certain direction. We need to reverse that inequality. We've got the rank of this thing is less than or equal to the desired quantity. So we need to reverse that. All right. Little trick, really. We can write I, the identity is I minus generalized inverse of A times A plus generalized inverse of A times A. So these two would cancel out. Theorem 3.3.6 would be applied right here on this inequality. We're going to say M equals the rank of the identity matrix. It's an M by M identity matrix, right? It was associated with here I minus an M by M matrix. So it's understood the dimension would be M by M on this identity matrix, I sub M. I use all my notation. So M equals the rank of that identity matrix. It's an M by M identity matrix. That identity matrix can be written as this vector sum and difference. All right. Is the rank of the sum less than or equal to the sum of the ranks? Sound familiar? 3.3.6. We bounce back to the notes again. 3.3. Right. Said exactly that. The rank of the sum is less than or equal to the sum of the ranks. It said some more stuff as well, but that's the part we want. Okay, rank of the sum, less than or equal to the sum of the ranks. Back to where we left off. Okay, I want to view this matrix added to this matrix. Rank of the sum is less than or equal to the sum of the ranks. Rank of the first one and rank of the second one. Okay, as observed earlier, we saw above in part 3 that the rank of the generalized inverse times A is the same as the rank of A. So we'll make that substitution of that number. And I think that reversed the inequality. Up here we had the rank of the identity stuff is less than or equal to, move it to the other side, M minus the rank of A. Here we've got the rank of the identity stuff. Let's see, it's on the big side of the inequality, so it's greater than or equal to M, move this to the other side, minus the rank of A, and that's exactly what you get out of it. So we can draw a conclusion of this type of equality or whatever, move the rank to the other side, that was the specific claim. So that justifies part 5. Back to 3.5 notes. Okay, so that gets us to that. Another theorem, shifting gears, talking about systems of equations. Says, let AX equal B be a consistent system of equations, and let this denote the generalized inverse of A. All right, new stuff dealing with solutions to a consistent system of equations, but dealing with it in terms of a generalized inverse. So we're going to make a claim rather similar to the kind of claims you make when there's unique solutions. First claim is, if we take X to be generalized inverse of A times vector B, the right-hand side, this is a solution. Yeah, that's maybe some more good reasons to call it a generalized inverse, the way it interacts with systems of equations. A generalized inverse can be used to find solutions to a system of equations. Our weak point now, pragmatically, is I don't even know if generalized inverses exist, and I don't know how to find them. We'll take care of that in the next section. We're just using, we're introducing some properties of them on the hope that they actually exist and we can find them. Also going to turn out they're not unique. Stuff for the next section. Let's see. Secondly, if we have X equals some matrix G times B as a solution to the system AX equals B for all B that are solutions of the system of equations, then we must have this relationship here. That is, G must be a generalized inverse. So not only do we get solutions using generalized inverses, but if we have a solution written as a matrix times vector B of appropriate dimensions, then that matrix must be a generalized inverse. Sort of an if and only if kind of thing. And there's a few more details to be dealt with, but sort of an if and only if type relationship in terms of expressing solutions to that system of equations. Next, if Z is any vector in Rn, then generalized inverse of A times B plus this thing here times vector Z is also a solution. All right. Wouldn't be surprised if we don't put some geometry on this pretty soon. This arbitrary vector that we're using, this arbitrary vector Z, I'm thinking that's probably taken some linear combinations or something or other here, probably the columns of this matrix. So we'll talk about that in a more geometric way before it's over with. In terms of confirming this claim about is a solution, it should be a piece of cake. We'll just plug it in and see if it works. Every solution of the AX equals B system of equations is of the form X equals what we were just talking about for some Z. So we're getting sort of an if and only if type relationship here as well. Let's see, let me look at the next note and then we'll go through the proof. In the textbook, at least the first edition of the textbook, they've stated this third part totally wrong. This is the correct statement. If you want an authoritative reference for it, there you go. I went to a book on generalized inverses and found it as an exercise in that book. Probably you can find this stuff somewhere online because I don't have this book. Amazon might actually have a preview of this book. It's just only on page 3, so it might have a preview of the first few pages. I don't recall exactly where I got that, but there's your reference to justify this. Though we're going to go through and work that problem because we're about to prove this stuff. Okay, so next, let's do a proof of that. We're claiming this thing is a solution to that system of equations. Well, let's plug it in and see if it works. We know A times generalized inverse of A times A multiplied by vector X equals A times X because A equals this vector. That's the definition of generalized inverse. So with AX equals B as a system of equations, we could take the AX part and rewrite it in terms of this. We'll associate the AX on the left-hand side together, and now we've got that A generalized inverse, AX equals AX. You know AX equals B from the system of equations, so we can substitute B in for the AX, and we get A generalized inverse of A times B equals other side equals B. Associate then these two, and we have A times something equals B. Well, that means that something is a solution to the system of equations. So that's what was claimed. Generalized inverse of A times B is a solution as claimed. All right, let's see. I might need this in the background as well, so it'll take us a slide or two more work to get through this. Next claim's a little bit more involved. If X equals G times B is a solution of the system of equations, and this works for all vectors B for which a solution exists. All right, so there may be vectors B that for which this system of equations is consistent, and there may be vectors B such as this system, such that this system is inconsistent. Well, we're only saying this can be done for all B for which, of course, a solution actually exists. So you're generating solutions like this, and this can be done for all B for which a solution exists. Then we must have that G is a generalized inverse of A. All right, so that's what we're showing next. All right, let the columns of matrix A be A sub 1 through A sub m. Notation you ought to be used to by now, because we've done this plenty of times. We're going to take B and show, remember B was the right-hand side in a system of equations, take B and replace it with these. The first one, then the second one, and so forth. Replace it with A sub j, where j is somewhere between 1 and n. Then we've got the system of equations, ax equals A sub j. I claim that's got a solution. Of course it's got a solution. Just take vector x to be a vector whose components are all 0 except for its jth component. Remember, ax produces a linear combination of the columns of matrix A with the components of x as coefficients. All right, make the jth component 1 and all the others 0, and it'll pick off that A sub j. It'll pick off that jth column. So indeed, ax equals A sub j has a solution for every one of the j's, for every one of the columns. All right, so we're looking at possible B values for which there is a solution. That's why we brought this into the conversation. We've hypothesized that every one of those solutions can be written in the form G A sub j for some matrix G. So G A sub j then is a solution of AX equals A sub j, and this works for the same G and all different values of the J. That was the hypothesis. In other words, A times this G times A sub j equals A sub j for j equals 1 to n. Remember what the A sub j's are. They're the columns of matrix A. So this reads A times G times the first column of A equals the first column of A. A times G times the second column of A equals the second column of A, and so forth. So we can just collect all these columns together on the left and the right. When you collect all n columns together in order on the left, you get matrix A. Do it on the right, you get matrix A as well. So this claim of equality for varying values of J produces A, G, matrix A equals matrix A. And that was the claim. In other words, matrix G is a generalized inverse of matrix A. All right, part 3. Let's look at the statement in the notes. Statement in the notes. Here we go. For any matrix Z, Rm, matrix, excuse me, for any vector Z in Rm, so a vector with m components, generalized inverse of A times B plus this times Z is a solution to the system of equations. So what we're going to do is substitute this in and watch it work. All right, so substitute that in. I don't know anything about Z, so the Z is going to have to disappear. Distribute, we get A times generalized inverse of A times B. A times, go ahead and distribute through on that second one, produces this familiar looking thing here. Let's see, part 1, we saw that A generalized inverse of A times B equals B. That was because a generalized inverse times B was a solution to the system of equations. So make that substitution, we get vector B here. Hey, A generalized inverse of A times A, that's A itself, definition of generalized inverse. You got an A minus A producing a 0 matrix, and we get B out. So A times this stuff equals B. This stuff is a solution. And right there is where the Z disappeared. So that works for any Z of appropriate dimensions. And finally, what was the claim? Let's jump back and look at the notes. Claim was every solution is of this form that we were just talking about for some vector Z. All right, Suppose y is a solution. We're going to show y is of that form, and it ain't going to take long. Okay. We can certainly write y as a generalized inverse of a times b minus generalized inverse of a times b, because those cancel out, plus y itself. All right. Let's see. We know y is a solution. That's what y denotes. So we get ay equals b. So let's take this b and replace ay for it. Done. All right. The rest of it remains the same. Ay equals b. Let's factor a y out of these rightmost terms. Be careful, there's a negative out front as well. So we'll factor a y out. We'll need an identity here. We'll need a negative sign here to keep the positive and negativeness balanced. And we pulled a y out, so we get a generalized inverse of a times a. And let's see, we can take the negative inside and change some signs, and we produce something like this. And that was the claim. So any solution is of this form as given here. Excuse me, I didn't explain what z was. We did make one additional substitution of replacing the y here with z. It said for some z this can be done, and in fact the z we're using is something sort of specific here, but that was the claim. Every solution can be written in this form for some z, and there you go. And that takes care of Theorem 5.3. Okay, we made this observation. Before we get into more rank and null space stuff, let's go ahead and cut things there, and we'll come back and do a second video and finish up the last part.